Anyone can build a website using Squarespace, the sponsor of this video. In 1870s, a young boy went to his physics professor and said, "Hey, I want to be a physicist." And the professor replied, "Physics is almost complete. Don't waste your time." Fortunately, that boy decided to waste his time and get a PhD because pretty soon we realized that physics was broken. You see, classical physics predicted that everything in this universe, including you, me, and donkeys, and that cup of coffee, should radiate infinite energy. At any temperature, it should give out infinite energy mostly in high frequency ultraviolet and X-rays. This later became known as the ultraviolet catastrophe. It was a catastrophic result. Clearly, it is wrong. Coffees do not give you infinite energy in high frequency X-rays and ultraviolet rays. Instead, they give out finite amount of energy, mostly in infrared radiation. And that's because the actual graph looks like this. Today we call this the black body radiation curve, and you can see it peaks and then it goes back down. At low temperature, that peak is mostly in the infrared region. Of course, at high temperature, that peak can go back to the visible region, and therefore at high temperatures, things can glow like your incandescent bulb and stuff. But the big question was, how do we fix this? How do we go from what the classical disastrous result that physics was giving us to the actual result? What needs to be modified to give us this answer? Nobody had any clue. Nobody was able to solve this puzzle. Nobody except for the man who wasted his time pursuing a physics degree, because he realized using trial and error and in later what he called an act of despair that the only way to solve this is to assume that energy is quantized. Yes, this man is Max Planck, who accidentally saved physics and then regretted it. We've all heard of this story multiple times, how Max Planck quantized energy and saved the day and solved this whole catastrophe. But the big question for me was how? I'm not talking about the math part of it, but what is the logic behind it? How does quantizing energy solve this? Well, that's what I've been trying to understand for the last few weeks, and I think I finally have the intuition for it, and I'm super excited to share that with you. So the goal of this video is not just to understand this, but for us to put ourselves in Max Planck's shoes, pretend we don't know anything about E is equal to h nu, and then rediscover it from scratch. So if you're ready for this, let's begin. So Planck, where do we start? Planck says, Mahesh, the first big question we need to ask ourselves is what really caused the ultraviolet catastrophe? I mean, there are a ton of details, but at the very core, what are some main reasons for it? Turns out there are three. The first one is we can simulate a black body, a perfect black body, as a hole in a metallic cube, because a hole is pretty much a perfect absorber, so it can also perfectly emit radiation. And now if you heat up that metallic cube, then its thermal energy will be stored in electromagnetic standing waves. Each of these standing waves represents a degree of freedom, an independent way of storing energy. But the thing about the standing waves is that you can set up any amount of standing waves of shorter and shorter wavelength. There is absolutely no limit to it, which means you can have infinite degrees of freedom. The second point is that not only do we have infinite degrees of freedom, but the degrees of freedom actually increases with frequency. And again, this is the reason. The reason for this is because we live in 3 dimensions. See, in 1 dimension, there's only one way to set up a particular standing wave. So there's only 1 degree of freedom per frequency. But in higher dimensions, for example, in 2 dimensions, as we can see over here, notice that if there are, at higher frequencies, if there are more lobes, then there are more ways in which you can set it up. And therefore, you will have more degrees of freedom at higher frequencies. So putting these two together, what we see is that at lower frequencies, meaning high wavelength, you have less number of degrees of freedom. But then as the frequency becomes higher and higher, the number of degrees of freedom becomes more and more and more. And the final piece of the puzzle over there was equipartition theorem, which suggested that at any temperature, the average energy per degree of freedom must be the same. So if each degree of freedom on average gets the same amount of energy, immediately you can see the higher frequency ones, which have more degrees of freedom, they end up getting most of the energy. And since there is no limit to it, that causes that disastrous curve. Now again, we've talked about this in great detail in our previous video, but again, you don't have to watch that if this summary makes sense to you. We can go forward, no need to break the flow over here. But Planck, now the question is, how do we solve for this? And Planck says, Mahesh, think logically. We know this is wrong. That means at least one of these 3 must be wrong, isn't it? And so Planck asks, Mahesh, which of this do you think is wrong? And I'm like, it has to be the first one. I mean, clearly that's the problem. There's infinity right over there. That's the problem, right? And Planck says, well, let's see. First of all, can you simulate a perfect black body as a hole in a metallic cube? The answer is yes. There's nothing wrong with that because a hole does act like a perfect absorber, so it's a perfect emitter. Nothing wrong with that. Now, if you heat up that particular metallic cube, then indeed the thermal radiation will be stored in the standing electromagnetic waves, which act like a degree of freedom. And now it is true that there is no limit to how short the frequency can be. You can set up any amount of standing waves of shorter and shorter and shorter frequencies. There's no limit to that, which means this is accurate. Indeed, you get infinite degrees of freedom, and that is accurate. And I'm like, okay, that is very interesting. What about the next one? Degrees of freedom increases with frequency. Well, we saw it, and that is also accurate. This is just math. There's nothing wrong with that. So that means there's only one option left for us which can be wrong. It is the equipartition theorem. It has to be wrong. And I'm like, how can it be wrong? It's a statistical law which says on average every degree of freedom should get the same amount of energy. It makes sense. And Planck says, yeah, and yet it has to be wrong because we know the other two are right. And so the next big question for us is that if that is wrong, we need to figure out why it is wrong and what is the new partition theorem? How do we figure this out? Planck says, here's the plan. Let's go back to the classical physics one more time. The same thing that we saw earlier. Less degrees of freedom, more degrees of freedom over here. And by the way, the numbers are just for representation purpose. They're not mathematically accurate, okay? Anyways, now let's look at what the actual graph was. It looks like this. And let's compare the two. What's interesting is that at higher wavelengths, the classical physics actually agrees with the experiment. That's interesting. It's at lower wavelengths, you can see classical physics starts overestimating. Of course, lower the wavelength, the overestimation becomes more and more and more. In fact, if you were to zoom in over here, you will see even here is an overestimate, but it's very small. So we can kind of get the picture. The classical physics is doing an overestimate. Equipartition theorem is an overestimate. But at higher wavelengths, that overestimation is small. But at lower and lower wavelengths, that overestimation becomes bigger and bigger and bigger, and that's why the graph ends up blowing up. So, since equipartition theorem is an overestimate, this means that in reality, the energy per degree of freedom on average must be less than E naught. E naught divided by something. We don't know how, we don't know why, but it has to be not divided by something so that we can humble this graph. But more importantly, over here, it's an excellent agreement, which means over here, it must be pretty much E naught divided by 1 point something. There is a small discrepancy. So it must be very close over here. The denominators must be very close over here to 1. But as I go shorter and shorter, the denominator must increase because the discrepancy increases. For example, when I come over here, the denominator might become 5. So that 100 E naught by 5 becomes 20 E naught, and there is a significant decrease, and that's how we can fix that point. And if I come even shorter, maybe the denominator becomes even more, and therefore the graph becomes more and more humbled. And then finally, over here, when I go to even left, the denominator becomes so much big that the product starts decreasing again. And eventually at very, very short wavelengths or very high frequencies, you have very high number of degrees of freedom, but maybe the average energy over there is pretty much 0. So the product goes to 0. This is how, if we have this kind of a partition theorem, then the graph can be explained. Does that make sense? And I'm like, yeah, I'm starting to get some intuition. I mean, over here, the average energy per degree of freedom is pretty much the same as E naught. Therefore, the product keeps growing just like what classically was predicted. But then the energy starts reducing, and so the growth is less than what is classically predicted. But eventually, the energy becomes so small that the product starts decreasing and then eventually goes to 0. What's interesting over here is it's kind of like what we did in our lab exams. Like, we didn't get the right output and then we went back and changed the numbers to try and fit it, right? I mean, I wasn't the only one who did that, right? But the big question now is, Planck, how do we explain this? I mean, equipartition theorem made statistical sense to me, right? Like every degree of freedom on average should get the same amount of energy. But now what's the explanation for this? And Planck says, well, Mahesh, quantization. Quantization is going to give an explanation. But I'm like, how? How does equipartition theorem gets transformed into this particular energy function just by introducing quantization? Well, Planck says it's kind of like how your ideas can be transformed into beautiful websites just by introducing Squarespace, the sponsor of this video. Squarespace is an all-in-one website building tool that can transform our ideas into beautiful websites like the one that I've built over here. But recently, Squarespace also introduced design intelligence, where it takes this to a whole new level. It has now integrated AI technology, so you can just tell it what your ideas are and it'll create a personalized website for you. Website building just became so much more fun. And eventually, when you're ready to sell some stuff like digital products or services or whatever that is, you can manage all payments now directly using Squarespace payments. And not just that, you can accept payments in various different popular modes. And to top it all off, you have this beautiful analytics section where you understand how your website is doing and you can use that to feedback and improve, which is awesome. But what's the coolest is that you can start for free just by heading to squarespace.com/FloatHeadPhysics. And yeah, if you decide to make a purchase, you can even save 10% by using the promo code FloatHeadPhysics at the checkout. The link is also in the description. Now back to understanding how quantization saves the day. Planck, how? How does quantization do anything? Help me understand. And Planck says, well, let's look at it step by step. First, let's take an example. Imagine you have a bunch of tennis balls just floating around at different heights. Then you'll have some of these balls with very low potential energies and some of these balls at very high potential energies, right? And therefore, there will be some average energy. We'll call that average energy as E naught. What's interesting over here is that you'll find more balls at lower energy, and as you go higher and higher, there'll be lesser and lesser balls. That's kind of like the air molecules, for example, over here. The air density is very high, closer to the ground, but as you go higher up, as the energy increases, the number of air molecules per volume starts decreasing. Okay, and the same thing applies to the standing waves inside our metallic cube. If you take any specific wavelength, it can have any energies, right? So the distribution would be, well, you will have all the possible energies. You will have the lowest energies and you will have the highest energies. Remember, energy of an electromagnetic wave only depends on its amplitude. So lower energy is low amplitude, higher energy is high amplitude. But the distribution would be, you'll find a lot of these waves at very low energy, and as you go up the energy, the number of these waves will start reducing. But again, what's important is that there will be some average value, and that average value is E naught. Now, classically speaking, classical physics says the same story should hold good for all other frequencies. So if you consider high frequency visible light, the same story, the distribution is the same, everything is the same. Remember, energy only depends upon amplitude as far as classical physics is concerned. It has nothing to do with frequency. So the same story holds for frequency, and so even for higher frequency waves, well, the average energy stays the same. Regardless of how high the frequency go, average energy stays the same, and this is your equipartition theorem, and this leads to the disastrous ultraviolet catastrophe. But now, let's introduce quantization and see what happens. Let's go back to our tennis balls over here, and we'll now introduce some levels, kind of like imagine you're introducing some planks in between. And we'll now put the condition that the balls cannot be hanging or floating in the air anymore. They have to be sitting on either the ground level or the first level or the second level or the third level, nothing in between. They have to be sitting over there. This is called quantization, and this minimum level size is what we call a quanta. Now, the moment we do that, it's kind of like the balls will now all fall down, right? So that's these balls will be on level 0. All these balls will be at level 1. You don't have anything in between, and so on and so forth. Now, when that happens, look at the energy. Each ball has lost some energy, and therefore Planck asks Mahesh, what happens to the overall average potential energy? Well, I'm like, since each ball has lost some energy, the average potential energy should be smaller than before. It should become smaller. But what's interesting is that since the quanta size over here is pretty small, I mean, you have a lot of energy levels available, the balls didn't have to fall much. They fell just a little bit, as you can see over here. And therefore, the change was not much. So although the average energy reduced, it didn't reduce that much. It's still pretty much same as E naught. But now, what if we go back and increase the quanta size? Let's double it, let's say, for example, over here. what happens now? Ooh, now the balls will fall more. And now, look, the average energy has reduced quite a lot compared to before. Can you see that? Because the balls had to fall more. So if the quanta size increases, look, the balls fall more, the average energy reduces more. And if we go back and increase the quantum size even more, the balls fall down even more. And look, the average energy now reduces considerably. And what if the quanta size was much larger? Then almost all the balls fall down and the average energy now almost goes to zero. So what does it all mean now, Planck? Well, Planck says, and this is the key insight over here, when we quantize it, the average energy becomes less than what classical equipartition theorem says. But what's interesting is that if the size of the quanta is very tiny compared to the average energy that classical equipartition theorem predicts, if that quanta size is much smaller than that, then equipartition theorem has pretty much no effect on it. You get the same average energy as the classical theory predicts because the balls don't fall down much. But if that quanta size becomes bigger and starts becoming considerably big compared to, the average energy that classical physics predicts, now the balls fall down a lot and the average energy starts reducing. Bigger the size of the quanta, smaller is the average energy. And eventually the average energy just goes to zero if the quanta size is just too big. And so Planck says, Mahesh, look at this. This is how quantization transforms the equipartition theorem's average energy. It reduces it, and the size of the quanta controls how much it reduces it. And I'm like, okay, how do we put this together to explain the graph now? And Planck says, yeah, I'm glad you asked. So what we can do, first of all, calm down. Let's calm down. But what we can do now, and let's see if this makes sense, okay? Over here, we want the average energy to be less than equipartition theorem, what predicted classically, but not much. It should be very close to it. It should be almost approximately same as equipartition theorem. So, Mahesh, what should be the quanta size over here? It has to be small. We need to have small quanta sizes over here so that it doesn't affect anything. But then as we get shorter and shorter, we want the average energy to be much smaller than what the equipartition theorem predicted. So that means we need the quanta size to become larger. So look what we need to fix this graph. To fix this, we need to introduce quantization of energy, and we need to make sure that the size of that quanta depends on the frequency. At low frequencies, the quanta size should be smaller. At high frequencies, that quanta size should be bigger. Does that make sense? This means as the frequency increases, the size of that quanta should increase. The quanta size should be directly related to the frequency. Does this make intuitive sense now? Because it's again kind of like what we used to do in our exams. Not only did we change the values, but now when the invigilator came, we have to explain to them why we had to change the values. You have to come up with a justification. Please don't tell me I was the only one who should do that, okay? But this makes sense, right? Of course, next part is purely mathematical to figure out the exact relationship, but at least it makes sense that the size of the quanta should be directly related to frequency. So Planck worked out the math after doing a lot of trial and error, and he figured out the best relationship that was actually giving the best result was a simple one: directly proportional. If the quanta size increases directly proportional, increases with a direct proportionality, then you get the same shape as the graph. And then it was a matter of, again, doing the math to figure out what that proportionality constant was to get the perfect fit. And that proportionality constant, he called it the Planck's constant. And again, what I find fascinating about this is you can see from the classical perspective, this does look like an act of desperation. I mean, we are introducing quantization, and then we are saying that the size of that quanta must be proportional to the frequency. You change with frequency. I mean, this feels like, what are we doing over here? I mean, we're just desperately trying to fit the graph, and that's exactly what Planck did. And he would be excused in thinking that this wouldn't have any broader significance, but oh boy, today we know that it did. But anyways, I'm getting ahead of myself. But now we can see this eventually is what E is equal to HF. This is where it all came from, because this is how it solved the graph. Okay, so let's put it all together to see if we have complete intuition for this, okay? going back to those wave distribution that we saw, if we introduce quantization, then at high wavelengths or small frequencies, the quanta size is very small. If the quanta size is very small, then look, there are so many energy levels available, they don't have to fall much. As a result, the average energy stays the same as what equipartition theorem predicted. But as the frequency becomes larger, wavelengths become smaller, the quanta size becomes larger because it's directly related to quanta. But again, if the quanta is too small, then again, you have a lot of energy levels available, and therefore the average energy doesn't change much. And therefore, equipartition theorem pretty much works at high wavelengths or smaller frequencies. But now if you reduce the wavelength a lot or increase the frequency a lot, now the quanta size becomes significantly larger. And so the waves fall a lot more significantly. And so now the average energy reduces significantly. And again, if the frequency becomes way more, very high, say we go to ultraviolet, now the quanta size is very big, and now the average energy waves fall pretty much, and the average energy pretty much dies out and goes to zero. And this is how the ultraviolet catastrophe is solved. So just making sure that we're on the same page over here, because this is really subtle stuff, okay? When you consider continuous energy with classical physics, you get equipartition theorem because there's no difference between different waves. Distribution is the same, everything is the same, average energy is the same, and therefore it predicts equipartition theorem, and you get ultraviolet catastrophe. But then we introduce quantization and make sure that the quanta size depends on the frequency. This is the key part. That ensures that at high frequency, quanta size is too big, and the quanta is so big that the waves do not populate a lot of energy levels, and so most of their energy just goes out. The average energy for high frequency just goes out to zero. Now we could stop over here, but it would be such a shame because I still have Planck with me over here, and I have my coffee, and we now have the opportunity to reap the benefits, the fruits of all the hard work we have done by asking one last question to Planck. Planck, why does the peak of that graph shift with temperature? Why is it at lower temperature, it's mostly in the high wavelength, and at higher temperature, it starts shifting towards lower wavelength? What's going on over here? How do we explain this? There are multiple ways to answer this question, and Planck says, well, one of my personal favorite is to look at things this way, okay? Going back to the graph over here, think of it this way. So at high wavelengths, the quanta sizes are very tiny. And when you have very tiny quanta size compared to the average, remember, average equipartition E naught, whatever that was, compared to that, if the quanta size is very small, then we can ignore the quantization effect, right? It's only when the quanta size becomes big enough, as I move to the left, when it becomes big enough, quantization kicks in, and then the graph gets severely humbled, okay? Now, what happens when we increase the temperature? When we increase the temperature, the average energy increases, so much more energy available. So what happens to the graph? Well, let's think about it step by step. Well, first of all, the whole graph blows up, and so we're gonna scale down the whole graph. So let's scale it down. But when we scale it down from this perspective, look, even the quantas over here have become much smaller. What's happening is that now this previously was big size, the quanta size was big, but now from this perspective, this quanta size is also very small compared to the new average energy now, because so much energy is there. Therefore, quantization will not kick in at this particular wavelength like it did before. I still have to travel more to the left before the quantization kicks in. Maybe somewhere here, now the quantas are big enough for that quantization to kick in, and now the graph gets humbled, and that's why the graph's peak shifts to the left. Did that make sense? I think it weirdly makes sense to me. So the same thing happens now at lower temperature. What happens if you lower the temperature? Well, now the whole energy, average energy, everything becomes much lower. And so now I need to scale up the graph to see this. So let me scale the whole thing up. But when I scale up the graph, now look, the quantization starts kicking in very quickly. Somewhere over here itself, the quantization kicks in because the levels, the quantas have become much bigger now compared to the average energy from this new level that we are looking at things from. And therefore, the graph will start getting humbled much more quickly. And so the peak will be in the high wavelength region. Again, I think it kind of makes sense, and if it didn't, it's probably because I didn't articulate it well. But think over it, and I think it'll probably make sense. What I find fascinating is that this is the reason why this coffee and you and me and everybody over here, we're all radiating a finite amount of energy, mostly in the infrared region, because the temperatures over here is much, much lower. It's only when the temperature becomes high enough, like that of the sun, that's when it starts giving out a lot of light in the visible region, and so on and so forth. So it's so beautiful. But of course, Planck had no idea what he had done. He thought he was just doing a math trick. He didn't think about any broader significance to the energy quantas. And yet he had no clue how to explain why energy must be quantized and why should it depend on the frequency and stuff like that. But it was Einstein who took this idea forward. And in this video, you can see how he actually introduced the idea, he took it forward, introduced the idea of photons, and actually got quantum mechanics started. All right, see you.